Hello, we will be modeling the buildup and effects of lead in children for our SCUDEM 2024 problem. Here's what we will be going over. The problem and assumptions. So what are we modeling and what is important to know? Our three different models, our analysis of our models. So what does our model say about the buildup of heavy metal? And the limitations of our model, or how could it be improved? Here are the questions that we would like to solve. What are the long-term patterns for an individual, and what is the impact for different levels of consumption? What happens to children who might consume a large amount of candy at certain times of the year? Will the trends be different for a child whose birthday is a long time before and after other major recurring holidays? And is there a difference if a parent has the children consume their treats over a long period after a holiday rather than allowing a child to binge during or just after that holiday? Here are a few assumptions to begin with our model. Children are otherwise healthy, no calcium or iron deficiencies, no broken bones, or malnutrition in any way. All lead is consumed and absorbed into the body through the bloodstream. Children are exposed to lead solely through contaminated chocolate and not by any other means. And each serving of chocolate has 0.375 micrograms of lead, which was the median amount found in our study. We first began with the in-out model and solved it to get this equation, which has parameters A, which is the amount of lead per serving, output parameter B, which is the amount of lead leaving the body, and C, which is the serving of chocolate consumed. This gives us a linear graph.
Obviously, a linear model is not the most realistic for our problem. So we created a half-life model where the output rate is the decay factor for the half-life of lead in the blood, which is around 30 days. Additionally, we turned our consumption parameter into a function of time to analyze the impacts of varying levels of consumption across the year. We used Euler's method in Python to solve our model going forward. For this specific model, we tried three different C of T functions. First, we used a sine function with a max consumption of 5 servings of chocolate and a minimum of 1. This gave us an oscillating graph for the blood lead content. We then used a square wave with the same max and min to represent constant eating over a certain period, such as the time following a holiday or birthday when a child might receive chocolate. We then tried a sawtooth wave to model what it would look like for a child who eats a lot of chocolate on a holiday and then decreases their consumption rate as the supply runs out. As we see from these three graphs, they have roughly the same shape and same levels of lead, but they model different consumption strategies of the child. For our final model, we sought to better match the research we had found by modeling the relationship between lead in the blood and lead in the bones. As we see in this diagram, we have lead coming into the bloodstream, then from the bloodstream it goes to the bones, or some of it goes out of the system, and then from the bones it can only go back to the bloodstream as it leaches out with its half-life. Our updated assumptions for this model are that all lead in blood either leaves the body or enters the bones. All lead in bones can only leave by leaching back into the blood, so only through the half-life can it go back to the blood. Lead in bones is inert, so it does not affect the system negatively in any other way, it just sits in the bones. And then children do not experience stress that causes excess lead to re-enter blood from the bones, such as breaking a bone. We came up with this system of differential equations to model this relationship, with the following parameters, most notably the half-life of lead in bones, lambda b, which is roughly 25 years, and alpha and beta, which represent the portion of lead that goes to the bones from the bloodstream. As we can see, we have our consumption function times the amount of lead per serving of chocolate going into the blood. From there, it is going to the bones by some proportion. From there, a proportion of it is going to the bones, and then from the bones, it slowly leaches back into the blood through the half-life, and from the blood, a different proportion is going out of the system through the half-life of blood. Additionally, we wanted to be able to see how different birthday dates relative to other holidays, in this case Halloween, impacted children's lead levels. So we created this periodic piecewise function where we can adjust our dates, consumption levels, and lengths of consumption. In this example, we have our birthday on day 200 and we are consuming 5 chocolates per day from both our birthday and holiday supply, which lasts us 4 days and 10 days respectively. In this example, we moved our birthday back to day 50 and raised our consumption to 10 chocolates per day over 2 days and 10 days respectively. In this one, our birthday is on day 150 and we are consuming 15 chocolates per day during both holiday and birthday.
For the purposes of analyzing our final model, we will assume that a child has 26.5 deciliters of blood and weighs 80 pounds. It is important to note that there is no safe level of lead in the blood. Blood lead levels as low as 2 micrograms per deciliter may not cause distinctive symptoms, but are associated with decreased intelligence and slower neurobehavioral development. But based on our final model, we can see several factors that influence the risk of severe lead poisoning. First off, we've modeled the birthday being at a different time than the holiday, Halloween. When we have those be on the same day, we can see that the risk of lead poisoning goes up a bit. The highest amount of lead in the blood does increase, but not by much. However, when we hold the amount of chocolate eaten constant, but increase the amount eaten per day, we can see that the highest level of lead in the blood almost doubles. This is still not a great increase compared to the final thing we looked at. Right now we can see that the amount of lead in 1 serving of chocolate is 0.375 micrograms. This is based off the median value in the study we looked at. However, if we change that to the max value, 3.136 micrograms, we can see that the micrograms of lead in the blood raises significantly. 200 micrograms in 26.5 liters of blood is a blood lead level of 7.54 micrograms per deciliter. A level of lead in the blood this large can cause anemia, severe damage to the brain and kidneys, blood disorders, and damage to the nervous system. This is the highest risk factor that we found when analyzing our model. We can also see that the level of lead in the bones increases quite a bit from this model to the next. That could pose a problem for longer-term health effects. We performed some sensitivity analysis on our model, and when we adjusted parameters, the model behaved as expected and remained stable, but our model still has limitations. Children may be in more danger than we assume based on our model because it assumes a constant half-life of lead in bones. This is not always true. Stress or broken bones can allow more lead to leach back into the bloodstream. Our model also does not take into account the difference between blood and soft body tissue, and so we don't model the effects of the lead in the liver or lungs. Our model assumes that children are not exposed to any other sources of lead, and this is unlikely. We also assume that all lead consumed is absorbed into the bloodstream. This is not necessarily true. Malnourished children who are iron and calcium deficient will absorb more lead in the bloodstream than a child who is not malnourished. In order to create this slideshow, we used Manim, and we referenced many different sources for our research. We'd also like to state our usage of AI, and finally thank the faculty at WLC, especially Dr. Tova Brown, and SCUDEM for allowing us to participate in this competition.